So a warm-up, although this one I don't think qualifies as a warm-up once you see the answer. It's about surface area, which is what we did last time. Find the surface area of the surface. Z equals square root 25 minus x squared minus y squared over the region in the plane x squared plus y squared less than or equal to 9. And we have some options here. 9 pi, 10 pi, 12 pi, 15 pi, 25 pi. Now before we get to the answer and before I ask for what the answers are, let's see if we understand what the problem asks. Do we recognize this surface? Sphere of radius 5. Now it's not the whole sphere. Which part of the sphere is it? The top half. So you have the top half of a sphere of radius 5. So we can just sort of do a sketch of some sort. It'll be a bit sketchy here. All right. Now we're not asking for the whole area of the sphere of radius 5, but rather we're asking for just a piece of it. So from -3 to +3. So our R, this is our R in the plane, and we're going up to the surface. So really it's this, what's it, cross cap? I can't remember the term for it. But it's just a piece of a sphere. So that's the surface we're after. It's just a top part of the sphere. Now, I claim one of these options we can eliminate just intuitively thinking about what's going on. Why can't it be A? Where does 9 pi show up in this picture? Yeah, 9 pi is this area. That's the area of R. So if the area of the surface were 9 pi, what would have to be true about that surface? It'd have to be exactly flat, exactly moved up. Because if it's not flat, you're going to add area. So are we exactly flat? No. So we know it's not 9 pi. All right, so now good, 1 in 4 chance. 10 pi, 12 pi, 15 pi, 25 pi. Did anybody work it out? Anyone want to guess? C? C sounds like a good guess, but B is the right one. 10 pi, just a little bit. Just 1 extra pi is all you got. So we have our formula for surface area, which involves taking 1 plus f sub x squared plus f sub y squared. And for spheres, it looks messy, but it's about as good as you can get for interesting surfaces. So we took the derivatives with respect to x and y, squared, added everything up, and we got this expression. So when we're trying to integrate for finding our surface area, we have to integrate this expression here. Well, x squared plus y squared is in our region, x squared plus y squared is in our function. We think polar. We swap the polar, and fortunately for us, there's an r on the outside that gets introduced, so we can do a substitution, carry through the substitution in the computation to get 10 pi. This is a hard problem. That being said, surface area in general is a very hard problem. And so when it comes to surface area, this is about as good as you can hope for. So the good news is, we're not going to do surface area that much. Or are we? Well, we'll get there. We'll get there. All right. I'm sorry. Were there any questions I should have asked? Okay. All right. So our thought for today, we thought we'd go classical. To climb steep hills requires slow pace at first, by our good friend Billy Shakespeare, or William Shakespeare. So this is sort of steep hills, analogy. If you're going to do challenging problems, you're going to be slow at first. And that's okay, you're learning. Don't think like, these take me a long time, I'm never going to get the hang of it. You will get the hang of it. It comes. You just have to keep working on it. So don't get discouraged by slow pace at the start. The more you practice, the better things will get. All right, so recapping from last time, this is going to be the exact same slide as last time. We were talking about surface area, And our basic idea is we want to find the area of this surface up here. Said, okay, all right, we do what we do for every problem in integration, break things into parts, understand each part. So we break things into pieces. So you take our little piece, you say, the surface looks a lot like a parallelogram. Great, we have tools for finding areas, namely cross product, and that led to the formula. Now, one thing I didn't write down, but I want to, and I'm going to do it right now, is this piece right here, we're going to give this a name. So going forward, we're going to call this DSA. So that's how we're going to think of it. So it's a bit of surface area. So when we talked about integrals, we sometimes use dA for a bit of area, dV for a bit of volume. I use DSA for a bit of surface area. Word of warning, the book does not use DSA. Do you know what the book uses? The book uses d sigma, which makes no sense. SA, surface area. That sounds better. All right. Well, let's try a problem with surface area. And most problems with surface areas tend to be of the setup variety because, as you can tell, for spheres, we said that was as good as you can get, and it wasn't that great. Okay, so setup, but do not evaluate an integral to find the surface area over the region 0 less than or equal to theta less than or equal to pi, 0 less than or equal to r less than or equal to 3. For the surface, z equals r cubed sine theta. Here, everything's in cylindrical coordinates. All right, so we can make some observations here. We can quickly sketch what's our region. So our region in the plane, we have 0 goes from theta to pi. So we're not going full circle, just halfway around. 0 less than or equal to r less than or equal to 3. What's our shape? Semicircle? Yeah, half a circle, semicircle of radius 3. So there's our region in the plane. Now, you say, great. We just have to do the following. We just have to set up our formula. And our formula, we have a formula. It's the integral over our region, square root 1 plus fx squared plus fy squared dA. Now, say, we're almost done. We have the formula, we have our region. We just have to find f sub x and f sub y. What's our problem? It's an r and theta, not an x and y. So, what can we do? Yeah, we have to change it. So unfortunately, surface area, the formula is in terms of Cartesian coordinates. So we have to change the problem. So we say, okay, let's start thinking r cubed sine theta. Well, let's break that off. R squared r sine theta. And you might say, why? Well, I should say, if you see a trig function, sine theta, cosine theta, you want to throw an r on it, right? Because then it becomes something. R sine theta? Well, I want to know what it becomes. That's why I'm asking. Come on, you knew I had to do it one more time. Yes. Okay, you're right. It's the variable y. What about r squared? X squared plus y squared. So our function in terms of Cartesian coordinates is x squared y plus y cubed. So updating, we have our integral over our region, square root of 1 plus, what is f sub x? 2xy. Take the derivative with respect to x. So this is our f of xy. 2xy, and then we square that. F sub y, x squared plus 3y squared. Great. And then we square that, dA. And we're almost done. what do we need to do to finish up the problem? The bounds, yes. And unfortunately, we can't use our nice polar bounds. We've got to go Cartesian. All right, dy dx or dx dy? I mean, you could probably just say, we'll get the answer either way, and that's true, but some ways are nicer than other ways. Dy dx, I like that. Where does x go from? -3 to 3. Now, given an x value, where does y go from? Well, where do you start? At the bottom. Yep, you always start at the bottom and then you work your way up. This is x squared plus y squared equals 9. So what goes at the top? Solve for y, good. And there's a square root of 9 minus x squared. Very good. And we're done. And you probably can see, yep, I would not want to integrate that. All right. Well, where are we going with this? Why talk about surface area? Well, we're trying to get to a type of integral. And so it's good to sort of step back and think about things that we've done before. So let's start by recalling things about arcs. So we learned a formula for arc length of a curve. So if I have a curve, start at some time t equals a, I start at a point, and I move to some time t equals b, and say, I want to find the length of that curve. There was a formula for that. It's the integral a to b square root of x prime squared plus y prime squared dt. And we used ds as the shorthand notation for s as being a little bit of curve length. So essentially, this is just a little length of the curve. Now, this is a formula for 2D. There's a similar formula for 3D, but I wanted to fit it on a page. So I did the 2D one. So a way we could think about that is arc length is just integrating along the curve 1 ds. We said, okay, but then we kicked it up a notch and said, let's not just do arc length, let's do line integrals. So we said, all right, so now we're integrating a function along the line. The function could measure different things. One thing we talked about is work. Another thing we could talk about is maybe it's a measurement of density, and we're trying to find mass. It just depends on what the problem asks. So how do you do it? Well, you rewrite the function in terms of your parameterization, and then the ds is your little bit of arc length. So we needed to understand arc length to get to line integrals. We're going to do surface integrals. So to understand surface integrals, we need to understand surface area, little bits of surface. So that's where we're heading. So generically, we have our surface area. We have a region R. Above it, we have a surface G. And we're asking the question, well, how much area is there in our surface? And we have a formula for that. So we say, okay, it's the integral of the square root. And this assumes that, I should have written down here, G is the surface. And it corresponds to the z equals f of xy over the region R. So I have this surface upstairs. We talked about how to find surface area. And we said, yes, this big long piece here, that becomes our piece of surface area. So we could just think about finding the surface area as integrating over our surface G of dSA. So we're going to move to surface integrals. So we're going to integrate on our surface some function, dSA. What do? We parameterize everything in terms of our region R. Just like we parameterized everything here in terms of our parameterization for t. So we get everything down to 2 variables. So we're pushing it from upstairs down into R. So we're pushing everything flat into R. We write the function so that everything is a function of x and y. And we have our bit of surface area. We have our expression for that. All right, so that's our goal. Find Find the surface integral. Okay, that can't be so bad, right? Any questions about the idea? It's the implementation that's where it gets fun. All right. Well, let's do a problem. Find the center of mass for the surface x squared plus y squared plus z squared equals 9, where z is greater than or equal to 0, given that there's a density function, delta of x, y, z equals z. All right, so let's first make sure we understand what our surface is. What is our surface? Well, it's part of a sphere. Which part? Right? We have this z greater than or equal to 0, so it's the top of a sphere of radius 3. So, okay, so we have this sphere of radius 3. Now, when we talk about the sphere, it's not a filled-in sphere, it's the shell. It's that candy coating, if you will. So we have this shell. Now, what's happening? It's not uniform density. The density changes. Where is it least dense? At the bottom. It's practically air. Where is it most dense? At the top. So it gets denser the further up you go. All right. Well, so that's our goal. Find the center of mass. Now, part of this question is going to be pretty quick. Can we say anything about the center of mass? It's got to be on the z-axis. Why does it have to be on the z-axis? Symmetry. So there's symmetry around the z-axis. And it's symmetry of shape, symmetry of density. So center of mass is on the z-axis. All right, so x bar equals y bar equals 0. So we're 2/3 the way done. Huh, that was quick. The other 1/3 might take us longer. Okay, so if we're looking for z bar, the last part, the z coordinate, how do we compute that? Take a moment to think about it. Oh yeah, there's a moment. Okay, that's involved. Someone mentioned mxy. Anything else? Mass. So it's a moment divided by mass. Well, which one should we try first? Mass. Okay, let's go for mass. So if I want to find mass, I would integrate on my surface what? When you're trying to find mass, what do you integrate? Density. So it's the integral of your density dSA. That's just very generic. So in our case, it's the integral. Our density is our z dSA. Okay, so, all right. Now, we're going to work over a region R. And in our case, our region R, let me see if, here we go, I'll use this color. It's, you might call it the projection, it's essentially, or the shadow. It's the part that it's on top of. So here, our region R, I don't have enough colors, and yet simultaneously too many. Okay, so R, x squared plus y squared less than or equal to 9. That's our R. We're going to have to spend some time doing our dSA, but not too much time because we did a little bit of this in our practice problem. So dSA square root 1 plus f sub x squared plus f sub y squared dA. Well, we have to solve for z, where z is the square root 9 minus x squared minus y squared. How much are you willing to trust me? I want to trust myself with that. But if you're willing to trust me, we'll just say equals, there's a little step here. 3 over the square root 9 minus x squared minus y squared. Okay. All right, so that's what it'll become. So that's your DSA. Oh, and then there's a dA added on to here. All right, cool. Let me just double check that I'm not crazy. This is what my problem. I'm always paranoid about things. Checking the notes. Yep, that's good. All right. So let's work out the integral. Okay, so this is the integral over our region R. What will z become? Well, so when we're in R, we've now pushed everything down into the xy plane. So I need everything to be in terms of x and y. So all z's have to be gone. So what does z become? Is there any clue, any guidance we might have on what z should be? Anything that tells us what z equals in terms of x and y. So something where if you gave us an x and y, we'd say, I can tell you a z. Anything? Not ringing a bell? Think about it like z is defining your surface. So it's like, what's the function that defines your surface? And then we can use that to replace z. Anything? Anything? Wait, you think there's something? Where? Oh my gosh. Oh, whoa. You're right. It was there. Okay. So we can replace z using our surface. So this is the square root 9 minus x squared minus y squared. Now, the DSA becomes 3 over square root 9 minus x squared minus y squared. So, does anything happen? Nice. Okay, so this becomes the integral over our region of 3. Well, I think we could figure that out. If you integrate 3, what do you get? 3 times what? 3 times your area. So if you integrate dA, you get area. If you integrate ds, you get arc length. If you integrate dSA, you get surface area. How much area is there in R? 9 pi. It's a circle of radius 3. So we get 3 times 9 pi equals 27 pi. Okay, so that's our mass. All right. Now, are we done? No. The journey continues. We're going to take a moment now. We integrate. When you do moments, what changes? What gets added? It's a distance. Moments are distance, density, and then, in our case, bit of surface area. So, integral over g. What is our distance to the xy plane? Z. So this distance becomes z. This density is also z. And then this DSA is still DSA. So we say, okay, that's the integral over our region of square root 9 minus x squared minus y squared, square root 9 minus x squared minus y squared, times 3 over square root 9 minus x squared minus y squared, dA. And good news, we get cancellation. Woohoo! Nice! And hey, we still have that 3 we can pull out. Nice! So what do we have? We have the integral over 3 times the integral over our region square root 9 minus x squared minus y squared dA. Now at this point you're like, oh my gosh, he's going to make us do an actual integral. Well, we could avoid it if we can think of what this integral represents. Don't worry about what it came from. Think about what it can represent. So, what can this integral represent? How can we interpret it? Again, ignore where it came from. You just have this integral handed to you, and you're like, oh, do you know what that is? And they're going to be like, what is it? And you're going to say, it's a and they're like, whoa, that means I can save myself a lot of work. It's not quite surface area. Sorry, what? Not arc length. And I know you're thinking of surface area, and that's why I'm saying forget where it came from. Put that out of your mind. When you were first introduced to integrals, you say, oh, all integrals represent area in 1D. In two-dimensional integrals, all integrals represent volumes. If you interpret that as a volume, what volume is it? It's the volume of the hemisphere. You're going up to the sphere. Now, do we know the volume of hemispheres? Well, some of us do, it sounds like. There's a half, because it's a half a sphere. 4/3 pi and r cubed, yes. And our radius is 3. So this is our very, we should make a note here, because people are going to be like, a second miracle occurred? What happened here? This is volume of hemisphere. Okay, well, can we simplify anything? We can cancel some 3's. We can put that 2 in. So what do we get? 54 pi. So what's z bar? 2. So, since this is the only real space left, our answer is 0, 0, 2. So we're 2/3 up. Does that seem reasonable? Sure. I mean, if we had gone that the z-coordinate was like 5, not reasonable. But 2 is not bad, especially because we know it's heavier at the top, because it's denser at the top. So there should be a bias towards the top. All right. So that was fun. So now to the real work for today. Any questions on our problem here?
When we get the first miracle, didn't get to
This miracle? Yeah. It's the same thing that happened from the review problem, where you take fx squared plus fy squared, and then it just turns out that you get an x squared over 25. In our case, it would be replace the 25 by 9, but it's the same thing. So there's an x that shows up here, there's a y that shows up here. You get x squared, y squared. When you add, this would be 25 minus x squared minus y squared over 25 minus x squared minus y squared. And then all your x squareds, y squareds cancel. So you just end up with the downstairs, you end up with what looks like the formula for the sphere. Upstairs, your radius. So that's where it was coming from. That was more than a bluff. All right. So we want to talk about flow. Flow through a surface. We talked about flow through a curve. And we said that's one of our interpretations of Green's theorem. But we want to get through flow through a surface. So we have some vector field, M and P. It's modeling movements. And so you can think of it as, say, fluid flow, air flow, whatever you want. Electrical flow, depends on your discipline. And we say, okay, we have a surface G. So there's a surface here. Here's our G. And our question is, we have this flow, this vector field that's moving through G. And the question is, how much actually gets through G? And now, keep in mind, flow can be positive or negative. So we want to find like the sum total flow. Now, to answer this question, we have to actually start by saying, we need to decide on an orientation for our surface. So we need to understand, we want to flow from one side to the other side, so we need to have one side be designated the top. Or just say, let's designate, here we use our normal vectors. Because if you think about normal vectors, we've mentioned this before when we were back in planes. Normal vectors aren't unique because you can go up or you can go down. So an orientation is just a choice of saying, which side are you on? So orientation says, I always pick the ones that are going up, whatever that might mean in context. Okay, so how do we find it? Well, basically you build up. Once you have your normal vectors, you say F dot n is the rate of flow. And I forgot to add a word here. Unit normal vectors, because we always want to make sure that we're going, we use unit vectors to indicate direction. So, all right, F dot n, that's the rate of flow. So if I'm going directly up through the surface, I capture all of the flow of F. If I'm perpendicular to the surface, nothing's going in or out. So you have to do this dot product. That captures how much of the flow actually is crossing. Now, that's your rate. How do you find your amount? Rate times area. So that's the amount of flow for a tiny piece of your surface. How do you find the total? You add it up. So the integral is adding up the little flows at every piece. Well, we already know that things get very messy with this DSA term. And probably things are going to get messy with our n term. So let's see what happens. If our surface looks like z equals f of xy, then how do you find vectors perpendicular to that surface? Well, we dig back and we say, how do we find tangent planes to surfaces? We use gradients. So if you take the gradient of z minus f of xy, that has to be perpendicular to your surface. And that's not a bad gradient to take. You get minus fx minus fy 1. Now, you'll notice here, I'm going to draw attention to this 1. What does that tell us about our vectors? If we see the z-coordinate is 1. They always point, in the z direction, we always move up. So you'll hear a lot of problems we'll talk about upward pointing. And it means positive entry in this coordinate. All right, so how do you find the unit vectors? Well, you divide by the length. And now you either get nervous or you get excited because you say, gosh, golly gee, we've seen that term before. Is that going to make it worse or better? Probably makes it better. What happens? Our flux, our vector field dot n dsa, so our vector field, MNP, dot n dsa. And almost as if it was meant to be, cancellation. So, to find flux of a vector field through a surface, it's the integral over the region that the surface is over, minus m fx minus n fy plus p dA. No square roots. Very easy. As long as you remember the formula. Now you might notice there's a box around this and some stars. This is that last formula you need before we head into the exam. So make sure you have this formula at your beck and call so that you can do well. All right. That's the theory. Any questions? We'll do an example. Okay. Find the flux for this function, f equals xi plus yj plus zk, for the surface with upward pointing normals given by z equals 1 minus x squared minus y squared above the xy plane. All right, so let's start by understanding our surface. What does z equals 1 minus x squared minus y squared look like? It's not a circle and it's not a sphere. It's what? Not a saddle. Someone said bowl. Yes. What about the bowl? Can you tell me more about this bowl? Upside down and up one. Yeah. So this is a paraboloid, but I prefer bowl. That just sounds easier to remember. So normally your bowl is going up. We go down, but we also shift up by 1. So let's say this is 1, and we move down. Now we only want the part above the xy plane, so we're not going to take the whole bowl. It does keep going downward, but we only need the part of the surface that's above. Okay, so there's our surface. Now, what's our region R? Because we're going to want to get to R. How do we find it? So this is our G, our surface. Where's our R? So to find R, imagine you look straight down the z-axis. So take your z-axis and pull it up. Look straight down. What do you see? Whatever you see, someone said circle. What, can you tell me anything else about this circle? Center at the origin. Radius 1. Whatever you see, that's R. So it's look down from above, and where do you cover in the xy plane? So you'll see the word projection. I think I've said the word projection once. But I guess it's okay for me to say things more than once. All right. So, good. We know our surface. We have our vector field. So now we pull out our formula. So if we want to find the flux, that's F dot N dSA. That's just the formula. Now we replace it by saying, but instead of trying to do a surface integral, we're going to do it by the region it's over. So we're going to put it all in terms of x, y. So even though this has x, y, and z involved, we're going to get it down to just x, y. So we're going to have our integral over our region of, and let's just start with the generic formula, minus m fx minus n fy plus p dA. And this is the hard part about the flux, is remembering that there's this formula here. So just remember where it's coming from. It's your F, M, and P, dotted with your minus Fx minus Fy 1, which this is from the gradient of z minus f of xy. So if you have to rederive it, that's where it's coming from. Probably don't want to rederive everything. It takes a while to go from Calc 1 to Calc 3 on the third exam. All right. So we start replacing things. Let's make notes as we go along. What is M? Yeah, X. So this is Mi plus Nj plus Pk. So it's X. What about F sub X? Well, this is your f of xy over here. That f is what's defining your function. So what is f sub x? Oh, and I forgot the minus sign. I'm sorry. There we go. Minus. Don't forget the minus. And there's a minus 2x. Minus, what is n? Y. Good. What is f sub y? Negative 2y. Plus, what is p? Z. Now, we should be putting here z, but we don't want to use z because we want everything in terms of x and y. So what do we put in? What the surface is. So every z that we end up with in here becomes that function, 1 minus x squared minus y squared in this case. Okay, so that's the answer. Well, for setting up, minus minus becomes plus, minus minus becomes plus. So what do we have here? We have the integral over our region. 2x squared plus x squared. 2y squared plus, 2x squared minus x squared, 2y squared minus y squared. So x squared plus y squared and plus 1. All right, so how would we integrate such a thing? Well, we're polar is the right? Because we're in a region, two-dimensional, so we don't think parametric. But we think polar because we see our favorite x squared plus y squareds. When you see x squared plus y squared, you start thinking like polar in 2D, or you start thinking cylindrical in 3D. So, in polar, what are we integrating? R squared plus 1, dA, r d theta. Theta goes 0 to 2 pi, r goes 0 to 1. Now you can break this up into two integrals, 0 to 2 pi d theta, and 0 to 1 of r cubed plus r squared dr. The first integral, no surprises, 2 pi. The second integral is 1/4 r to the 4th plus 1/3 r cubed. Evaluate that from 0 to 1. And when you plug in 0 to 1, plug in 0, you get 0. Plug in 1, you get 1/4 plus 1/3, also known as 7/12. Yeah? 3/12 plus 4/12. So you get 2 pi times 7/12. You can do a little bit here, so you get 7/6 pi. Now, can flow be negative? Yes. So don't get to the end and be like, oh, I got a negative answer, I must have done it wrong. No. Flow can be negative. It can be positive. I mean, we're asking how much is going through the surface. Sometimes it might be going in the opposite direction. It's going the wrong way. So be careful.
That r, the first step, should be r cubed plus r.
Oh, did I make a mistake? Oh, that's what happens when I go fast. You're right. It should be r cubed plus r, which makes this a half, which makes this 3/4 times 2 pi. So what does that make it? 3/2 pi? Nice. We should have everybody do that. Like on an exam, we'll have just come up, do the exam in front of a live studio audience. All right. An even nicer answer. All right. Well, we have a few minutes left. And I happen to have a multiple choice problem here. You can try some of this out. Let G be the part of the surface, Z equals y squared minus x cubed, lying above the region R, which has x goes 0 to 1, y goes 0 to 1. Find the flux for the function 2y arctangent z squared plus 3x squared arctangent z squared plus 60zk through the surface G, where n is the upward pointing normal, and the answer is going to be one of 1, 2, 3, 4, or 5. Before I let you loose, let me just make one observation. When you see pieces that look like this, what is that usually an indication of? That something's going to happen. that, you know, you're not going to do the naive thing. You're going to be like, let me go through and something's going to make that disappear. So this is like a good thing on a test. If something looks really bad, you're like, I don't think I want to do it the way it's asking. It's like, no, we don't want you to do it the way it's asking. We want you to apply the theorems. What happens with your arctangent terms? They properly cancel. You know, they weren't necessarily because of various issues, but they properly cancel here. Oh, whoops. What do you think the answer is? 5. Oh, you guys are amazing. Yeah, so they do cancel. So it's really the integral of 60z. But z is y squared minus x cubed. So you're integrating y squared minus x cubed over the square. And life is not so bad. That's something that's reasonable. So flux problems aren't as bad as they look. Just make sure you know the formula. One last comment. This is for upward pointing normals. If you ever see something that says downward pointing normals, what do? Change the sign. It's an orientation change, put a minus in. That's all you need to do.